Welcome to ECE 165. This is a lecture on dynamic logic. So we're going to consider this a new section title. So let's go ahead and write that down, dynamic logic. Let me go ahead and double box that. It's a section title. And if you're following along at home, the West and Harris book has a section on dynamic logic. That would be in section 9.2.4. And the Rabai, Chandrakosson, and Nikolic book, if you want to read that for more information, would be section 6.3. Okay, so what is dynamic logic? Well, I'm going to say what it's not. So unlike static CMOS, which is what we've been studying all along, which has direct connections to VDD or ground. So unlike normal static CMOS, which is what we've been discussing all along, dynamic logic, as the name may imply, relies, no comma there, dynamic logic relies on temporary or dynamic, hence the word, storage of logic values on capacitors. So what does this mean? The best way to understand what this means is let's go ahead and look at an example. Okay, so let's imagine we had some voltage source and it is connecting via some sort of switch, namely a transistor, and this connects to some sort of capacitor. Okay, so let's call this capacitor C. This is V out over here. Now, what I'd like to do is leave a little bit of space next to the C. We're going to draw something there in a minute. Okay, so bear with me. So in the meantime, let's go ahead and draw the timing diagram for what happens here. Okay, so we have T. This is the position of the switch. If we're drawing a 0, then nothing's happening. And if we're drawing something high, then the switch is on. And then we go back to 0, so the switch is open in that situation. Okay, so we say the switch is closed when the value of this logic here is positive or high in this timing diagram. So what happens to V out? Okay, so this is V out. All right. So prior to when the switch is open, prior to this all happening, we actually don't know what the value of V out is. Okay, so in fact, I'm not even going to bother drawing it. We don't know what the value is. It turns out we will have a way to do this moving forward, but let's just say we don't know. All right. Now, when the switch closes, we know that the voltage will rise up to whatever that input voltage happens to be. Okay, so if this is, V in, then this will rise to V in. All right. Now, what happens when the switch closes? Or I'm sorry, when the switch opens back up? When this switch opens back up, well, there's nowhere for the charge on the capacitor to go, so it should just, sit there, like so, okay? And this is really the basis of dynamic logic. It's that once you charge a capacitor, unless there's some mechanism by which charge will leak away, that logic level will stay there for, forever, unless there's a path to leak that away, okay? So unfortunately, there is a path for this to leak away, so we never have capacitors just sitting there in the ether, not connected to anything. There's going to be some degree of parasitic resistance through subthreshold conduction, gate leakage, and so on. Let's call this R leak. Okay, actually, that should, if I'm following my own color code, that should be in red, R leak. Okay, so what ends up happening if we kind of extend this timing diagram out to a long time is eventually this will slowly start to decay until it reaches 0 in this scenario. Okay, so what we say here is that this would expect to stay indefinitely except for our leak. Okay, because our leak is there, it is going to eventually discharge this voltage all the way to zero if our leak is indeed connected to zero. So this turns out to be the biggest challenge, or rather one of the biggest challenges in dynamic logic, is that the logic values are only valid at certain instances in time. And when we're designing our digital system, we have to be aware of when these instances in time are in order to design these circuits correctly. So now that we understand the basic principles of dynamic logic, we're storing logic values on parasitic capacitors, let's go ahead and draw a general dynamic logic gate. Okay, so a general dynamic logic gate. Okay, so it turns out a general dynamic logic gate is fairly straightforward. We have a PMOS at the top, not surprising. Our output comes out here. Output is, say, equal to Y. We have some function, which we'll describe later, and then an additional NMOS transistor on the bottom here. Okay. Now, this NMOS and this PMOS are connected together, or the gates are connected together, and the input signal here is what we call phi. All right, we'll get into what that means momentarily. Now, the logical inputs into this function are given into this function f here. Okay, so what's going on here? So first of all, let's call this function f. This is actually going to be the same pulled down network as before. Okay, so if we know how to design a pull-down network in static complementary CMOS logic, this will be exactly that, except only the pull-down, not the pull-up. On the PMOS side of things, we have this device here called a pre-charge switch, or pre-charge transistor, I suppose. And on the NMOS, below this function, we have what we call an evaluate switch or transistor. Okay, so how does this circuit work? The circuit works in two phases. Okay, the first phase is what we call the pre-charge phase. This is when phi is equal to 0. Okay, when phi is equal to 0, the bottom evaluate switch is off. The top PMOS is on. Okay, so what this means is that the pull-down network is off because that bottom evaluate switch is off, and the pull-up network, which is just that PMOS, is on, and therefore Y is pre-charged to VDD. Now, we should note during this case that the output in this case, Y, is pre-charged to VDD. So other nodes in the pull-down network may be pre-charged because they're comprising of NMOS transistors to VDD minus VTN. Okay, so that would be the case if, say, for example, the gate inputs into the NMOS transistors in the pull-down network were on. Because Y is on, that's going to charge some of these internal nodes to VDD minus VTN, ignoring subthreshold leakage, of course. So that's phase one. The next phase, if the PMOS switch was called the pre-charge switch, then the next phase ought to be called the evaluate phase, and indeed that's the case. Evaluate. This is when phi is equal to 1. Okay, so in this phase here, one of two things happens. Okay. Option A, I suppose. If the pull-down network is on, then Y is driven low. just like it would in a static complementary CMOS circuit. All right. Option B is otherwise, if the pull-down network is not on, then there is no DC path to the output, right? The PMOS, that pre-charge switch, that's no longer on. The pull-down network is not on. Even though the evaluate switch is on, the pull-down network creating function F is not. So there's no way to pull it down to the pull the output down to ground. There's no DC path to the output in this configuration, so therefore the charge stored on Y remains there. Okay, noting that there's always a little bit of parasitic capacitance on every node here. Okay, so in a general dynamic gate, what we do is we pre-charge the output to VDD. During this phase, the logic function is not operating. There's no function being evaluated here. Okay, it's only during the evaluate phase when phi goes high, the pre-charge switch turns off. If the pull-down network is active, then Y will be pulled down. If the pull-down network is not active, then Y will remain high. Okay, so this is the way that we compute logic functions using dynamic logic, noting that the output is only valid during the evaluate phase. During the pre-charge phase, the output is not valid. So now that we understand how a normal or a general dynamic logic gate works, let's go ahead and talk about the simplest possible gate. That would be a dynamic inverter. Okay, so a dynamic inverter looks something as follows. We have our pre-charge PMOS transistor. This creates our output Y. And then on the bottom, we have two NMOS transistors. One is the input, and the other is connected to this clock signal that we are calling still, in this case, phi. Okay, so this is what a dynamic inverter looks like. Now, the best way to understand how this dynamic inverter works, and frankly, the best way to understand any dynamic logic circuit, is to draw a timing diagram. So get used to drawing timing diagrams because we are going to be doing it all the time. So first, we'll start with clock phi. It'll look something like this, goes high for a little while, then low, high, low. This is just a normal clock signal, so it goes high and low alternately with a 50% duty cycle. Now, when I'm evaluating a dynamic logic circuit, I like to be very clear with myself when I'm doing so and just very clearly indicate what region or what mode of operation the device is in. When phi is low, we're in the pre-charge phase. When phi is high, we're in the evaluate phase. Okay. Now this is perhaps obvious, but I like to just indicate this when I'm doing homework problems and exam problems and so on to help make things extra clear for me so I don't get confused. All right. So what we're interested in doing is trying to analyze basically the behavior between these important intervals here. Okay, so let's just put some dotted lines. This helps with our timing diagram analysis. Okay, now let's further say that input A looks something like this. It's 0 initially, and then it goes high somewhere over here, and then it stays high for the rest of the cycle. Okay, so what does output Y look like? All right, so one thing we can do, because I've indicated where the pre-charge phases are, we can just directly draw in the pre-charge results. We know during the pre-charge phase, Y should be equal to logic 1. So we can just directly draw that in. All right. Now, all we have to do is fill in what happens during the evaluate phase. All right. In the first evaluate phase, we see that A is equal to 0. So that NMOS transistor is off. The evaluate transistor is on, but transistor A is off, and so therefore there's no way for Y to be pulled down. So therefore Y is just going to hang out where it was before. Okay, so we call this dynamic storage of logic 1. Okay. All right, so that's 1/3 of the battle. Let's now look at the next pre-charge phase. So you'll note, interestingly, during this next pre-charge phase, that A goes high during this pre-charge phase. But that doesn't matter to the output because the output is, well, pre-charging, right? So A goes high, but that evaluate NMOS transistor is off, so there's no way for Y to go low. That is, until the circuit ends up in the evaluate phase. In the evaluate phase, that evaluate NMOS transistor is going to turn on. A is now on, so now there is a direct path to connect the output to ground. Okay, so this goes low after some delay. And then in the pre-charge phase, it goes back up. Okay, now A is still low in the next evaluate phase, so it's going to go down, back up, down, assuming that we go into another evaluate phase over here, and so on and so forth. Okay, so again, let's just be extra clear here. This is driven low by the pulled down network. Okay, so a couple things to observe here. One is that when the output of a dynamic inverter is supposed to be 1, the node doesn't switch at all. It just stays there, just like it normally would in a normal static CMOS inverter. However, if the output is supposed to be 0, because we have this pre-charge phase, what this effectively means is that the output now toggles between 0 and 1 as we go through the evaluate phase, back to the pre-charge phase, back to the evaluate phase, and so on and so forth. Okay, so if you are concerned about dynamic power, CV squared F times alpha, alpha in this case is rather high if the output is constantly a 0. So that may not be desirable depending on the application you are working in. In fact, I would say that under most scenarios, dynamic logic is rather power expensive because of this high activity factor. So you might be asking yourselves, why the heck would we use it if it has higher power? Well, it turns out there's a very good reason to use this, and we will discuss this momentarily. So before we get into the analysis of how effectively dynamic logic works, I want to make sure that we all know about the one rule we must follow. Okay, so there's one rule you must follow about dynamic logic. Okay, and it's important. So we wouldn't emphasize it as the one rule if it weren't important. Okay, so this rule says that during the evaluate phase, the inputs to the pull-down network are only allowed to do the following. They can either, A, go from 0 to 1. That's rather straightforward. Or option B is be stable. Okay, so in other words, i.e., there's one missing condition here, they are not permitted to go from 1 to 0. And you might say, well, that's kind of a rather imposing rule. When we build logic, we'd certainly like the logic to go from 1 to 0 sometimes, right? Otherwise, how do you do computation? So we'll address that in a moment. But before we do that, let's understand why this is an important rule. So here's why. Okay, and again, as I suggested, we are going to draw a timing diagram to understand this. Okay, so let's imagine that this is phi, we're 0, 1, 0, 1, back to 0. Okay, and let's imagine we have an input A and it goes like so, and then it does something like this. Okay, so that's actually breaking our rule. So remember, oops, I'm just going to, I don't know how that happened. I'm just going to go ahead and draw in where the evaluate phases are happening here. So let's go ahead and compute what happens to output Y in a dynamic inverter as an example. Okay, so when A is 0, we expect the output to be high. In fact, it should be high because of the pre-charge phase here. Okay, now when we get into the evaluate phase, A is still 0, so therefore the output remains high. All right, but at some point during this evaluate phase, A goes high. All right, that's going to drop the output to 0 and then back up when we re-enter the pre-charge phase. Okay, so this is outputting a 0, which is correct. Okay, so far so good. All right, now what happens in the next phase? As soon as we hit the evaluate phase, our output goes to 0, and that's good. That's correct. Okay, so far so good. But now input A goes from logic 1 to logic 0. Okay, so that pull-down network is turning off during the evaluate phase. In normal static CMOS, if the pull-down network turns off, then the pull-up network should turn on, and that should pull the logic level up. Okay. However, this is a dynamic logic circuit, and that does not happen. Okay, it stays low because there's nothing to pull it back up. All right, so this is the reason why we don't do this. Okay, so this here is incorrect. This is not a valid computation that we're doing here. All right, so this poses a bit of a problem. And to understand this problem, let's consider an example. Does the following circuit work? Does this circuit work? Okay, all I'm going to do, something very simple, is I'm going to take a dynamic logic inverter. Okay, so this is just a normal dynamic logic inverter. This is gate phi, this is input A. Okay, so I haven't done anything crazy here. And I'm going to connect it to another dynamic logic inverter in Cascade. So all I'm doing here is I'm putting two inverters in Cascade. Okay, and so when I draw the clock signal going through here, I don't mean that it's connecting to the bulk, I just mean that it's the clock signal going through here. So what I'm going to do is I'm going to take this guy, call that B, and take that to the output Y. Okay, so the question is, does this circuit work? As I mentioned, the best way to try and understand this is to draw a timing diagram. So let's say we have a pre-charge phase here, pre-charge phase, and then we enter the evaluate phase, and then back down to the pre-charge phase. Okay, so let's just, again, to be very clear about what's going on here, label that as the evaluate phase. I'm just going to draw some dotted lines here to make accounting of when things happen a little easier. So let's imagine that A obeys the rule. Okay, A goes high during the evaluate phase. It goes from 0 to 1. That's okay by the rules that we've established. Okay, so what does B do? Well, B is initially pre-charged. And I suppose actually this is actually a mistake here. Oh yeah, we don't know where A is coming from, so it could be from some non-dynamic logic circuit as an example. Okay, so in this case, B is pre-charged. When the evaluate phase happens, B will hold steady at logic 1, and then after a short delay, it's going to fall. Okay, and then when we re-enter the pre-charge phase, it goes back up. All right, now let me just annotate where this happens. So we have a delay from A heading into B through that inverter structure. All right, so far so good. Everything is working fine. Now what about Y? Well, Y was pre-charged during the pre-charge phase, so that's good. B is high, so after a small delay, in this case it's actually coming from the edge of the value of the clock to the output Y. Y will go down, but now that Y is down, there's no way for Y to come back up during the evaluate phase. It only can come up during the pre-charge phase. And so there's an instant in time here when we are getting the incorrect value. In fact, we're violating our rule. Okay, so does this circuit work? The answer is no. Okay, it violates our one rule. You know, we're not asking much. It's just one rule. Just obey by this rule. But this circuit, taking two dynamic inverters, putting them back to back, fails. Okay, so what we require is monotonicity. And we're not getting it with baseline dynamic logic. Okay, so we spend a lot of time thinking and working on dynamic logic only to find out it doesn't work. At least it doesn't work without some important modifications. So we just finished saying that dynamic logic in its nominal form doesn't actually work because if we take one dynamic gate and we attach the output of that dynamic gate to the input of another dynamic gate, it violates our one rule. Okay, so obviously we're not talking about dynamic logic for no reason. There is a solution to this. So the solution is something called domino logic. Okay, so how does this work? So first we notice that we can only have zero to one transitions at the input to our dynamic logic gates, and we only have 1 to 0 transitions at the output. Recalling that at the output of a dynamic logic gate, the value either stays high, it stays pre-charged, or it falls to 0. It never goes from 0 to 1 at the output. Okay, so there's a very simple solution here. The solution is to put an inverter, a static inverter, between the outputs of your gates. Okay, so it would look something like the following. We have our normal dynamic logic gate. We have some pull-down network function that we're computing down here. And then we have our NMOS footer device here. So again, this is the clock signal phi. We have some inputs into our function in this pull-down network here. And we note that these inputs only go from, I guess, 0 to 1 at the input here, which means that our outputs can only go from 1 to 0 at the output. So the idea here is we take a normal static CMOS inverter and use this as the inputs to some other pull-down network. Okay, in a dynamic logic circuit that is largely the same, or is the same overall structure as the previous stage here. And again, when I draw the input going through here, that doesn't mean it's connecting to the bulk. I'm ignoring the bulk in this drawing. I'm assuming it's just connecting through. Okay, so what this will do is going through the static CMOS inverter, it'll create a signal that goes from 0 to 1, which indeed abides by our one rule. Okay, and then of course at the output here we have another inverter, which means that this signal is falling from 1 to 0, and this signal is rising from 0 to 1, and so on and so forth. Everything is perfect. Okay, here are perhaps some other inputs that satisfy these same rules. So here, what we say is that dynamic outputs fall in succession. Just like dominoes. Okay, so in other words, what we're saying here is that all of the dynamic logic gates will get pre-charged to VDD, and then if a gate ends up falling, or rather if the output of a dynamic gate changes, the only way it can change is it's going to fall. Okay, so if it falls, then that will go through an inverter and create a rising edge. And then after that rising edge, you'll go into another dynamic logic gate, which will create another falling edge, and so on and so forth. Okay, and I just realized that I believe I spelt the dominoes here like the pizza chain, not as actual dominoes. Okay, there we go. So I'll make another note here. Note, there's some interesting things we can do here. The static inverter used between the domino gates is usually designed to be a high skew inverter. Okay, why? Well, we only have one type of edge coming in. We have a falling edge at the input coming in, and therefore we only have a rising edge at the output coming out. Okay, so we usually use a high skew inverter for better rising edges. Okay, now to be fair, we will enter the pre-charge phase, and at which point we could have a falling edge. But it turns out that for domino logic, we care less about the timing of the pre-charge phase because everything kind of happens in parallel with the pre-charge phase, whereas in the evaluate phase, things fall down like dominoes, and so we care much more about the timing of things during the evaluate phase. So one question you might be asking yourself as we've been going through this whole process of dynamic circuits is, why the heck are we doing this? You know, we started with this dynamic concept. It seemed interesting, and then we said it didn't work, and so we had to introduce domino logic. And now with domino logic, we need to create a dynamic gate plus a static gate. It seems like we're really, you know, making things more complicated than they ought to be. So it, of course, turns out there's a good reason that we are studying and talking about this, but let's discuss this. So why bother with dynamic circuits? All right, so again, there are good reasons why we're doing this. Okay, so let me write the good reasons in green. So first of all, we only require, or it requires, n plus 2 transistors per logic function. Okay, now that's true for purely dynamic logic. Of course, for domino logic, that becomes n plus 4 transistors, where of course n is the number of inputs. But this is much better in some cases than for static CMOS, which requires 2n transistors. If you have n inputs, you need n NMOS devices and n PMOS devices. Note, in contrast, pseudo NMOS still actually wins. It only requires n plus 1 transistors. But of course, pseudo NMOS has all sorts of problems with static power consumption and so on. In addition, the load parasitic capacitance is small. Because we have fewer transistors, we have less load capacitance. This is great. Unlike pseudo NMOS, there is no static power here. Okay, so recall that during the pre-charge phase, when the PMOS device is on, the NMOS footer is off, and therefore there's no current flowing through that. That's unlike pseudo NMOS, where the PMOS is always on, and whenever the pull-down network turns on, there's static current flowing through the circuit. Okay. In addition, this is non-ratioed logic. So that means it doesn't matter how you size it, the circuit will still be functional. Okay, it may not be optimal in terms of performance and timing and energy and so on, but it will be functional. Okay, and most importantly, dynamic logic is fast. Okay, so let's try and understand this for a bit. So the propagation delay low to high is, well, we have this pre-charge phase. So if we ignore the pre-charge phase for just a moment, the propagation delay from low to high is 0 because we've already pre-charged. There's no computation that needs to happen. We already have the right answer. Okay. That's of course ignoring the pre-charge phase, which you do have to consider as part of your timing analysis here and so on. But anyways, if you ignore that, this is fast. The propagation delay from high to low, we're going to say is, well, small. Okay, smaller than static CMOS. Okay, so we say in the end, overall, when you factor in all of the overhead, we say it's say something like 1.3 to 2x faster than static CMOS. Okay, and that's the main reason why we use dynamic logic, is because it's faster. Okay, but there is no free lunch, so we have some downsides. So let's make a little sad face. So first downside is we have high activity factors. Okay, this results in high power. So dynamic logic is fast. However, there's a price you pay for that speed, and that's in terms of power consumption. In addition, we have a downside related to noise. Leakage is a problem. We have to refresh logic values and so on. There's charge sharing issues that we're going to talk about momentarily, etc. So there's a whole host of problems. If you want the most robust computation, static CMOS is the way to go. And in fact, it's pretty energy efficient. It's pretty fast. Most designs today use static CMOS. However, there is utility here. The main utility of dynamic logic is that it's fast, right? So this was previously, a variant of domino logic was used in microprocessors in the 90s and early 2000s. Okay, so that was true when those computers were trying to, get as many megahertz as they could, and power consumption wasn't as large of a concern, and so on. So nowadays, this is largely replaced with or by static CMOS. So most microprocessors today are implemented using static complementary CMOS. However, again, if you're designing something and you need to get the best energy efficiency possible, the best speed possible, dynamic and domino logic or a family of domino logic is still possibly the right choice. With all of that being said, this style of dynamic logic is still used in memories and specialized applications, mostly for area efficiency. As we'll get discussing in memories, it turns out that area is the #1 criteria when we get into those designs. So as we alluded to in the last slide, there's a lot of good reasons to build dynamic logic circuits, but there are also several issues. Okay, so let's discuss these now. The first issue I want to discuss is one that we've actually already alluded to earlier, and that is leakage. Okay, so let's just say already introduced, just to be clear. All right, so this is happening from subthreshold leakage, diode leakage, and so on. Let's just say it's most mostly from subthreshold leakage, but it could be gate leakage, diode leakage, and so on. Ultimately, what this does is it limits the minimum frequency of our circuit. This is a strange concept to think about in relation to our previous discussions, where we're always focused on the maximum possible frequency we can operate our circuits at. But with dynamic logic, we also have a minimum frequency. So let's just take a look at a small example here. So let's plot, as we are tending to do now, a timing diagram. So let's say that we have a clock signal. It looks something like this. Something like that. Okay, this is perhaps not how we would normally build a clock signal, but for the purposes of this example, it'll do. All right, and then let's go ahead and plot V out of a dynamic logic gate. Okay, so let's just imagine in the prior clock cycle we had totally discharged our output, so we're at 0 here. And then when the clock goes low, we enter the pre-charge phase. So we charge all the way up to VDD, everything is good. And then when the clock gets released and the pull-down network is not active, because of leakage, we're going to start trending downwards here. Okay, and so I'm going to say that we want to make sure that we don't pass some threshold limit. This is debatable what this should be, but let's just say for this example, we don't want to cross VDD over 2. Because if we cross past VDD over 2, then we've definitely lost our logic value. For more robustness, this threshold should probably be larger than VDD over 2, but I think it's a reasonable baseline case for us. Okay, so we say the point where we hit this VDD over 2 threshold is going to define the maximum period, or alternatively the minimum frequency that we can operate at. Okay, and then this process will continue as shown here. Okay, so if we were to clock our circuit at a slower frequency than this, leakage would basically totally disrupt the logic stored on the capacitors in our dynamic circuit. Okay, so therefore, this means we effectively need to recharge or refresh every node in our circuit, once a clock period. That's setting our minimum frequency. Now, of course, there's still also a maximum frequency. We can't clock the circuit too fast, otherwise we get into propagation delay issues. Okay, so this is an issue. Is there a solution? Well, of course there's a solution. There's always something we can do. One possible solution to this problem is something called a keeper transistor. And this is actually something that should look familiar to you. So what we do is we have our normal dynamic logic circuit. We have our pull-down network. Then we have our NMOS footer device. PMOS and the NMOS are connected together. This is the clock signal phi. All right. There's some inputs into this pull-down network. Okay, so the issue with our domino logic is that this dynamic node, let's call this Y here, can fall because of leakage through the pull-down path here. Okay, so I leak. We don't like that. Y is supposed to stay high if the pull-down network is not active. Okay, so the solution is actually very clever. Okay, so let's say that's output Y, this is output Y bar here. Okay, so let's take this output here, and what we do is we feed it back through a PMOS transistor. This is called the keeper transistor. Okay, so let's just put an arrow here, keeper transistor. All right, now this should look very familiar to you. When we discussed pass transistor logic, we suggested this as a way to get rid of that VT drop across the NMOS pass transistor. So what happens in this case? So if y is equal to 0 and y bar is equal to 1, then what happens? So y is equal to 0, so the output y bar is equal to 1, that PMOS transistor is off. And the output stays at 0 through the pull down network. Okay, so the pull down network is pulling y to 0. That's a strong low impedance connection to ground. It's going through the inverter, which is causing y bar to be at 1. Everything is good in this scenario. There's no problems. Situation 2 is if y is equal to 1 and y bar is equal to 0, then at this point, so y is equal to 1, it's supposed to be staying high, but the pull down network through leakage mechanisms might be pulling y low, and we don't want that to happen. However, y is 1, but y bar, as needed in our domino logic circuit, is 0. That turns on the PMOS. PMOS is on now, which combats the leakage from the pull down network, keeping y in the logic high state. Okay, this is excellent. All right, so this totally solves the problem. However, note, let's just make a little note here, that this is now ratioed logic. Since the pull down network must be strong enough to overpower the PMOS when it wants to turn back on. So the solution to this issue is we make the PMOS weak. Remember that PMOS only needs to combat the leakage. So the PMOS has to be stronger than the leakage path through the pull down network, which is going to be, admittedly a rather low amount of current. All right, so if we generally want to make that keeper transistor a minimum size PMOS, not even size 2 per the class sizing convention, a size 1 PMOS. Okay, that's as weak as possible. And the pull down network, if it's properly designed to have an effective resistance of R, should be able to overpower that PMOS and bring Y low when it needs to on the next cycle. Okay, so this is a very nice solution to this leakage problem. So let's discuss the next issue, and that's a little nefarious one called charge sharing. All right, so the best way to understand how this manifests is to look at an example. Let's look at a dynamic 2-input NAND gate, a NAND 2 gate. Okay, so let's just go ahead and draw it first. So we have our PMOS header. We have our pull down network, which is just 2 series NMOSs followed by our NMOS footer. All right, so the gate looks something like this. This is our clock input phi. This is input A. This is input B. And our output here is Y. Okay. Let's ignore the inverter after this. We can analyze this without looking at that inverter. So what I'd like to do is I want to point out that on node Y, we have some parasitic capacitance. We'll call that CY. Okay, but we also have some parasitic capacitance at an internal node in the circuit here. Let's call this node X and this capacitance CX. Okay, now let's imagine that during this example, input B is equal to 0. All right, and let's say that Vx was equal to 0 initially. So perhaps in the prior phase of the clock, the pull down network had pulled everything down, and Vx was equal to 0 in this example. Then we say A goes from 0 to 1. All right, so what happens? Let's take a look at our timing diagram. So let's say we have phi here. Let me do my timing diagram in a different color. Phi, let's say, goes like this. Okay, and A, we say, goes 0 to 1, somewhere over here. B, we've said, is just 0 all the time. Hasn't changed. Now let's look at node Vx. Okay, so we said that Vx was 0 initially. All right, let me just draw a little vertical line here to help us. We said that Vx was 0, and when the clock turns on, that will continue to be true because A is 0, B is 0. So node X here is not changed at all when the clock goes high and we enter the evaluate phase. However, once A goes high, what happens? The output Y is nominally at what value? Let's just draw this down actually, Vy. All right. During the pre-charge phase, the output Y is at logic 1, right? Now, as soon as we enter the evaluate phase, let me just draw a vertical line here just to be extra precise. As soon as we enter the evaluate phase, nothing happens to node Y because the pull-down network is not on, despite that footer NMOS being on. Okay, so as soon as transistor A turns on, what happens? So this continues here. As soon as transistor A turns on, well, node Y was charged to VDD, node X was charged to 0, and we've just turned on a switch that connects these two. Okay, so what's going to happen is there's going to be charge sharing. All right, so we can draw the circuit that, models this. We have node X and node Y, CY, CX, VX, VY, and we basically just close this switch. All right, and so what's going to happen is the charge on VY, which was charged to VDD, is going to share with the charge on CX. So what's going to happen is node VX is going to go up a little bit, not all the way. Likewise, Vy is going to go down a little bit, not all the way to 0, but just a little bit. Okay, and so what we say here is that this distance here, if you will, is equal to delta V. Delta V. Okay, so let's just write that down in words. When input A is asserted, the transistor turns on. We'll just call it a switch in this example, and we're ignoring a VT drop and so on. The switch turns on, and CX and CY share charge. Okay, so we can say that after A goes to 1, we say that the node Vx is equal to Vy, ignoring our VT drop, if that is applicable, which is equal to VDD times the charge sharing capacitance formula, which is Cy over Cx plus Cy. And we're going to say that's equal to delta V. Okay, let me put a little asterisk here and just say careful if V out ends up becoming less than VTN, because then we have a threshold drop across the NMOS device, and this formula isn't totally correct because it's no longer acting as a good switch. All right. So it turns out that if Cx, the value of the parasitic capacitance, is approximately equal to Cy, which is not a crazy assumption, then the output drops significantly. All right, possibly to the point where it may no longer be a logic 1, at which point we have a disaster. Okay, so we really don't want the output simply because one of the other inputs that's not causing the output to fall, by the computation of the logic function decreases. Okay, so we really don't want the output to decrease other than when the pull-down network fully turns on. Okay, so this is definitely a problem. So there has to be a solution to this. So the solution that we're going to suggest here is to use extra pre-charged transistors. So what we do is, as the name implies, we have our normal pre-charged transistor here. We have our NAND gate structure down here, and then our footer device. Okay, so this is our normal dynamic logic gate. So far, nothing has changed. This is A, this is B. Okay, this is the output Y. So the idea here is it's the charge sharing at the node between A and B that's the problem. So why don't we just go ahead and also pre-charge this node to VDD. If we pre-charge that node to VDD, then if the same scenario happens that we described in the previous slide happens here, then when switch A turns on, Vy is already charged to VDD. Vx is also charged to VDD, so there's no charge sharing. They're both at the same voltage. Okay, so this works. It solves the problem completely. However, this has more parasitics. We're adding parasitic capacitance onto node X here. More devices, and therefore area. More clock power, because we have more capacitance on our clock net and so on. So there's some downsides to doing this. Now the other solution that we could have done is let's just make sure that Cy is much larger than Cx. And nominally that should be the case, right? Cy is, has the extra PMOS attached to it. It's driving a load and so on. It turns out that that load is in domino logic is usually just one inverter, so it's not, a huge load, but it's definitely a load nevertheless. So usually Cy is larger than Cx. And we don't have to do this sort of thing unless in very special circumstances. We are introducing it in the lecture because this can and does affect dynamic logic. And so if it does, be aware that this is A, a problem, and B, there are some solutions to it. So there's another nefarious issue that can crop up in dynamic logic, and that has to do with capacitive coupling. Okay, so again, the best way to understand how this manifests in dynamic logic circuits is by means of an example. So let's imagine that we have a dynamic inverter. Okay, so it's dynamic because we have this extra clock terminal that's coming in here. So we'll call this a dynamic inverter. And let's imagine that this is driving some long wire somewhere on the chip. It's loaded by some inverter somewhere else. Actually would probably be loaded by some logic. But we have some load capacitance associated with the output of the dynamic inverter. And then somewhere next to this circuit, we have a static CMOS inverter. Okay, and we know that it's static because there's no clock coming into it. So this is a static CMOS INV, and we're going to call this the aggressor. Okay, so this is also driving some long wire on the chip. The wire has some sort of load and so on. Now these wires, for layout reasons, happened to be very close to each other. So as a result, there is parasitic capacitance between the two wires. We'll call this CC. Okay, so for example, from parallel plate, 1R in parallel, wire capacitance. Okay, the wires are routed close to each other. Okay, so in this scenario, let's imagine that V out is nominally, being held at VDD dynamically. And then let's imagine that this aggressor was at VDD and all of a sudden it switches down to logic 0. So it's So it was at logic 1 and now it's at logic 0. So let's go ahead and draw a circuit model that describes this scenario. So we can model our aggressor as a voltage source that is driving a capacitor that's driving another capacitor. Okay, so this is CC, this is CL, and this here is V out, and the input here is coming from VDD to 0. Okay, so just to be clear here, this is describing the scenario. So CL, we say, was originally floating at VDD. It's just sitting there floating, in its happy little space. It's a high impedance node. The pull down network of that inverter was not on. It's just sitting there. Okay. So what happens here is the aggressor, the static CMOS inverter, is pulling down the line next to it, the wire next to it. That capacitively couples into the output of the dynamic inverter. And we can actually write an equation that describes what would happen here. The voltage on V out after the switching event would be VDD times VDD minus VDD times CC over CC plus CL. Okay, so again, what might happen here is you might get a situation where V out is just hanging out, and then when this edge happens, it's going to come down a little bit. Okay, it's going to come down by an amount equal to VDD times CC over CC plus CL. Okay, that's the delta V. So again, if we say that if CC is approximately equal to CL, this can affect functionality. Right, we definitely don't want this delta V to drop too much. All right, so therefore the conclusion here is that layout, particularly when we're talking about dynamic logic, although this applies to all other forms of logic, is very important. You really have to be careful about how you are doing your layout to make sure that you don't have any unnecessary parallel plate capacitance that might adversely affect your dynamic logic circuits. Okay, this is a very important point. Now, I do want to make a note. Static CMOS is more immune to this due to the resistive connection to VDD or ground. So the reason why dynamic logic is so affected by this is because the output is just floating there in the evaluate phase if it's set at VDD. If the output is at ground, it's being strongly held down by a pull down network, so this actually isn't a problem. But in static CMOS, that's always the case. So let's just take a look at a little example. Let's imagine we had the same scenario except in this case, we don't have a dynamic node, but we have a static CMOS node. Okay, so everything's the same, CCCL. The input is going from 1 to 0. Okay, but now instead of just having this floating capacitor, we now also have a resistor that's going to VDD, and that resistance is R on of the PMOS device. All right, and just to be clear, this here is V out. All right, so if we do have a event where we have this aggressor here, then what's going to happen is V out, it's playing happily at VDD. There's going to be some perturbation. It's going to go down, just like it did in the dynamic case. But because that resistor is strongly pulling things up, it's eventually going to pull it back up to VDD, where this voltage here is VDD. Okay, so in other words, static CMOS is restoring. We'll get a glitch on the line at V out, but it won't drop and then stay there like it does in dynamic circuits. Okay, so this is a big advantage of static CMOS design, is it's indeed much more robust to coupling and noise and so on and so forth. So another issue we may want to discuss is the notion that normal domino logic has limited logic styles. I guess this isn't really a downside in the context that we haven't considered this a downside for normal static CMOS, but I suppose we're listing it as a downside because eventually we'll have a solution to this. But the issue at hand is that domino logic only performs non-inverting functions. So for example, because we have that extra inverter at the output, we're only building AND circuits, ORs, and so on, but not NANDs or NORs, and so on. Okay, so this may or may not be a problem depending on the type of logic that you're trying to build, but if it were, there is a solution to this. So a solution is something called dual rail domino logic. Okay, sounds fancy. Let's figure out what this is. So what it looks like is as follows. We have our PMOS header switch. We have our pull down network. I'm going to describe this as F bar in this case. And then what we do is we have another PMOS header over here. This goes into a separate pull down network of function F, and then these two guys combine to finally have our NMOS footer switch here. Okay, so this footer switch is driven by clock phi. Same thing for these PMOS devices, also driven by clock phi, so they're connected together. In other words, all of our inputs come in over here. They also go into the other pull-down network. And then we have our inverter that goes to output Y, and another inverter that goes to output Y bar here. Okay, so this is what we call a dual rail domino logic circuit. So it actually looks pretty similar to our Cascade voltage switch logic family that we introduced a while ago, but in this case, this is effectively the dynamic version of it. And the advantage of building a dual rail domino circuit is that we now compute both, say if we're doing an AND function, we're now computing both AND and NAND. Okay, and that is possibly of use depending on the type of computing application that you're building. So I think it's best to try and understand this logic family again with an example. And in fact, let's go ahead and just build that exact thing that I was talking about on the previous slide, a NAND and an AND function together in one gate. All right, so it's going to look something like this. We have our PMOS header, and then let's go ahead and build the NAND gate first. So it looks something like this. We have A, B. This is connected to the clock phi. This is going, the output here goes through an inverter, and this is equal to Y is equal to A and B. So again, that's the NAND function here. Then we have the other side of the circuit that's going to do the complementary function. So this will be something like this. Okay. And then we have our single NMOS evaluate switch here. These transistors are B bar and A bar. This PMOS pull-up is connected to clock phi, and this goes through a static CMOS inverter to generate Y bar is equal to A and B bar. Okay, so how does this work? If A and B are both equal to 1, then the left side of the pull-down network will turn on during the evaluate phase, which will cause Y to be equal to logic 1. Because the internal node discharges to logic 0. If you look on the other side of the circuit, if A and B are both equal to 1, then A bar and B bar are both equal to 0, and so that pull-down network doesn't turn on, and therefore the output of that pull-up network was pre-charged to VDD, and so Y bar in this case is going to be equal to 0. All right. Now we do still have this issue of charge sharing, okay? And so normally we had to go through the inverter to get the charge sharing mechanism kind of sorted out. In this case, with our dual rail domino circuit, we can do something slightly more clever, and that is to build a cross-coupled PMOS pair. Okay, so basically what we do is we take the output of this PMOS, connect it to the gate over there, and so on. Okay, so these are what we refer to as let me just spell it out, cross-coupled keepers. Again, it looks similar to the Cascade voltage switch logic family that we discussed earlier, but in this case, it's doing this through positive feedback, which was the same case before, but now with no static power consumption, because we have the footer switch and the header switches that are acting in the right time. Okay. Now, you might have thought that we needed 2 NMOS footer devices for each branch, but it turns out we don't, since the pull-down networks are mutually exclusive. Or in other words, what we mean by that, only one is on at a time. We can use one device here instead of what we would nominally require as 2 to save area and power. Okay, so this type of circuit, this dual rail domino with the cross-coupled keepers and so on, this circuit or the logic family that this circuit represents was used in many generations of Intel microprocessors. Famously in the Pentium 4, actually was also used in the Core 2 Duo line, etc. Okay, it stopped, my understanding anyways, is that it stopped at the Core i5, i7 line, okay, where they reverted back to static complementary CMOS. So these circuits are extremely fast. That's why they were used in a lot of these microprocessors, though, as we've discussed, very costly in power. So just be aware when you're building any form of dynamic circuit that power consumption can be rather high. So please just do keep that in mind.